A family is going camping for a week and will be taking their pet with them. They can only find room for 5 kilograms of food for their pet and will bring only 2 types of pet food, type X and type Y. Each kilogram of type X food has 10 grams of fat, 9 grams of carbohydrate and 12 grams of protein. Each kilogram of type Y has 15 grams of fat, 9 grams of carbohydrate and 6 grams of protein. The pet will need at least 30 grams of fat, 27 grams of carbohydrate and 24 grams of protein for the week. The constraints that we've just talked about can be written as inequalities. One constraint is missing. Write the missing constraint as an inequality in terms of x and y in simplified form. So what we need to do is identify which ones we've got here. Well, we've got the non-negativity ones just here. The x plus y is less than or equal to 5. That's got to be to do with the fact that they can only take 5 kilograms. Now, 27 grams of carbohydrate. This looks like the carbohydrate one. Let's just check. 9 and 9. 9 and 9. Yep. This one here with the 24 looks like it might be to do with protein. So let's just check the protein. 12 and 6. 12 and 6. So we're going to have to do the fat one. So that's going to be 10x plus 15y needs to be greater than or equal to, the pet needs at least that, so it's greater than or equal to 30. Now we can divide through by 5. They want a simplified form. So that's 2x plus 3y is greater than or equal to 6. The inequalities are shown on the graph below. We want to add the missing inequality and shade the feasible region. Now our missing inequality was 2x plus 3y is greater than or equal to 6, which means the boundary line is 2x plus 3y is equal to 6. So if x is equal to 0, y is equal to 2. If y is equal to 0, x is equal to 3. So it's going to be a line that goes through these points like so. And so this is the missing constraint just here. Now, we know that we have to be below this one, and these ones we have to be above. So the feasible region is going to be this one just here. We now want to determine the optimal amounts of each type of pet food to minimize the cost and state the minimum cost. We can see for X it's 20 cents per kilogram and Y is 30 cents per kilogram. So our cost function, which we could do in cents or dollars, I'm going to do it in cents, but I need to remember that. So that's going to be 20x plus 30y. And now what we need to do is identify the vertices of the region and be systematic about this. So vertex and cost. So my first one I'm going to say is 0, 5, and then let's work around in an anti-clockwise direction. So we've got 0, 4. Then we've got this one here, which is at 1, 2. Then we've got this one here, which is at 3, 0. And finally, we've got this one over here at 50. So at 0.5, that's 20 times 0, 30 times 5, that's going to give me 150 cents. This one's going to give me 120. This one's going to give me 80. This one's going to give me 60. And this one will give me 100 cents or $1. So the minimum is this one here. So x equals 3 and y equals 0. And the cost is then 60 cents. To ensure a large amount of type Y food, by how much should the price per kilogram of type Y food fall to maintain the minimum cost from part C? So we want more Y. Now this was our best vertex just now. To get more Y, we'd switch to this vertex just here. So the cost function now needs to be 20x plus ky, because it's this cost here that's changing. And what we need is for the cost at 3, 0 to be equal to the cost at 1, 2. Note the change in the cost here won't change this one because there is no y here. So we've got 20 times 3 equals 20 plus 2k. So 40 equals 2k. So k is equal to 20. So it needs to fall by 10 cents per kilogram.